Good noon, everyone. I'll be presenting about non-destructive inspection of casting from on behalf of my team. I'm Monishita Dev, Role 27. My companions are Role 28, 29, and 49. The first thing about inspection is the organized way of evaluating something. From engineering perspective, it includes measurement tests applied to an object. It may be casting, finishing, accuracy of the dimension, presence of any kind of defect, and mechanical and chemical tests. NDT or non-destructive testing is a way of inspecting something or evaluating a casting object about casting quality. The first thing about NDT or non-destructive testing is it evaluates the property of casting without damaging it, and it finds, locate a size and tells about the size of a flaw, and a little amount of sample preparation and surface preparation will be needed, and it is way too much rapid. It can go smoothly both with large casting and smaller casting, and finally we can contact with it in manufacturing processes also in service period. And another thing is it is indirect method. We cannot predict it with certain value, so reliability of this method is high, sometimes can come into question. Other than NDT, there could be others casting inspection method like destructive test, which actually completely fails the material and study that hardness, tensile, impact test are a way of evaluating this. But matter of irony is NDT cannot actually predict values or cannot conduct tests like this, which is highly important for casting materials, provides important casting properties. Among the method of casting, these are the some: visual inspection, radiographic, magnetic, dye penetrating, ultrasound, eddy current, thermography, and acoustic. First thing is visual inspection. The first thing we do while inspecting something, we actually inspect it with our eyes. Depending on the severity of the casting, we then reject it or take it for further inspection. So it is the first thing to do among all. And the things that can be inspected here: the presence or absence of any kind of oxide or corrosive deposition, cracks and their orientation, mechanical damage, dimensional accuracy, discoloration, distortion, other things. But if our eyes fails to detect this, we can take help of optical instrument, and this optical instrument, while evaluating, should be must in focus. And microscope, boroscope, holography, these are the things that can be used in this process. The second one is dye penetration test. It is a picture of contaminated workpiece. Then the surface of this workpiece is cleaned to eradicate rust, surface deposits, and then dye penetrating or dye. Dye actually sprayed on the surface, and finally, then we wait for some time, and the workpieces rinsed there by water or other solvents. And then after some time, we add some powdery white colored developer and wait for some time, and finally the colored dye can be visualized there. Advantages of this process are it can be used for a wide range of materials. It is fast and less costly, and complex kind of shapes can be inspected there, and it is portable. We can use it both in lab and in field. Limitations could be it's only the surface breaking defects can be detected here. Those lies beneath the surface remains undetected. Pre-cleaning is must. The surface cleaning is, if the surface cleaning is not good enough, then the spreading of the dye shouldn't be must could be go wrong. Machining may inhibit detection, and finally post cleaning is necessary. Third one is magnetic particle inspection. This process can inspect both surface and subsurface defect, and electromagnets are used here. It can detect casting like ferrous alloy, cobalt, nickel. This is the arrangement of the total system, and finally we get a picture like this under UV, revealing cracks. So how does it work? Firstly, magnetic fields are applied there, and if there is any crack, then magnetic flux leakage occur. Then A suspension of magnetic particles is sprayed onto the substrate and it substrate. Because of the flux leakage, magnetic particles in the suspension accumulated on there and indicating there's a crack and also magnetic flux leakage. This is well visible under UV light because in the suspension we add some pigment material and much more visible in under UV ray and in dark room. The advantages is good for casting, ferrous casting, and it can reveal surface and surface defects, and it can detect cracks, tears, voids, slag, inclusion, porosity, and finally, the problem that is experienced in dye penetrating because of sandblasting can be overcome here. The bad things are it only can inspect casting of non it cannot detect casting of non-ferrous aluminum, magnesium. This kind of non-ferromagnetic casting is not possible to detect here. Aluminum is also widely used casting material, and coating or plating on the casting need to be removed here. Subsurface crack below the 0.6 inch from the surface is difficult to detect here, and finally the residual magnetic field may give some faulty result. The third one is radiographic inspection. The name suggests there is a source of there's a radiation source and it transmits electromagnetic radiation through the casting, and the casting is placed before the recording film. This recording film. This recording film actually shows a image with different brightness, revealing the presence of any kind of defects or changes in medium. The wavelength of the radioactive source affect a lot. The higher the short the wavelength will mean the penetration power will be higher. For heavy metal casting, we use high energy X-ray beam. For light metal casting, we use low energy. It's a picture used during this process, and we can see these changes in brightness, and mostly these are white, and there's some small dark signs. It actually reveals there could be any presence, there could be any defects there. This another one picture is a picture of a bus. It shows differences or changes in medium. For aluminum casting, it is widely used, and the defects that lies in parallel to the X-ray beam is not good to defect with this process. And there's a standard depending on the section thickness and radiation source used. We can say, or we can choose the radiation source we need to. The advantages is any kind of material can go with it. Minimum surface preparation will be required. Both surface and subsurface defects can be detected here, and it gives a permanent record. We use a radiographic film. The limitation could be it's very expensive. Setting up time will be lengthy. We cannot deal with it in outside. And firstly, strong safety precaution will be necessary. Lastly, safety precaution should be strong enough. We are dealing with radioactivity, which is very harmful. So the preparation, the protection should be very strong. And finally, we fail to detect the crack that lies in parallel with the electron beam. Then eddy current. Electromagnetic flame is generated around the coil while uh, passing electricity through it. This electromagnetic magnetic field will introduce secondary magnetic field if there's a conductor, and that secondary magnetic field will result in a circumferential current known as the eddy current. So how does it work? When there's no discontinuity or crack, the amount of current will give a fixed value. But if there's any crack, the path of the eddy current will decrease, and will decrease the current value, indicating the presence of discontinuity. We can see the path of the eddy current is same here, but the path is higher in length than the normal or defect-free sites. So the key is to measure the difference in current. This is a phenomenon working behind. Eddy current isn't uniform throughout the section. It is highest at the surface, and with the increasing depth, the amount decreases. But at the depth, if where the amount is 37% that of the surface, it is considered as a standard penetration depth. And if the material's thickness is way too much low, the eddy current will be distorted, where leading to faulty errors. For eddy current, the conductivity of the material or the casting that we are examining is important. If the conductivity is higher, the induced current will be higher, and the secondary magnetic film induced in here there will be higher, and it will start to oppose the primary magnetic field, resulting in depth of penetration. So to overcome this, we have to reduce the coil's frequency, that will result in depth of the penetration. And other things that can affect the conductivity is the hardness, temperature, residual stress, and presence of other conductive material there. The advantages is heat damage surface cannot be examined here. Changes in casting structure also can be detected here, and it is highly faster, and both magnetic ferromagnetic can be detected or inspected here, which was absent in radiomagnetic or magnetic particle. Limitations are only electrically conductive materials can be used here. If the variable is changed, it cannot be dependable on multiple variables, and the thickness limitations is there. We have seen it in skin effect, and finally, it is only applicable for AC field. The next one is ultrasonic inspection. In this process, we use a transducer. It actually sends a signal and analyzes the reflective signals and gives the output like this in oscilloscope, and analyzing the magnitude of the magnitude and the shape of the signals, we actually can detect if there's any fault or crack. There are two ways of judging this inspection. One is through transmission. In here, across the thickness of the material, we use a sender and a receiver transducer. It sends the signal, and receiver receives it and analyzes this. But if there's any obstacle, the receiver fails to detect it and give a different kind of signal. For pulse echo, there's only one transducer. It itself sends and receive the signals and analyzing it, it gives a plot like this. For the back surface, the magnitude is higher, but for the signal deflected from the crack is lower in magnitude. And we can use it for detecting porosity, gas or shrinkage cavities inclusion in castings. And another problem is that coarse grained particles are not actually not actually good for this inspection method. Actually, they scatter signal way too much, gives error in result. And finally, also the thickness of the material must also be considered. Advantages, it could be the surface and subsurface defects can be detected here. Depth of penetration is much higher accuracy in determining the flaw position. Previously, we have checked eddy current, magnetic particle, or radiation. Those actually told about the position of the flaw, but couldn't predict how much depth the flaw existed. And finally, it is automated system and completely rapid. Limitation is not all materials can respond to ultrasound, and special training required. Irregular surface or cast irons and other coarse-grained materials are unresponsive to this, and cracks lying in parallel with the beam may go undetected, same as the radiographic inspection. And finally, the guideline of process. For surface inspection in any kind of material, we can go with visual inspection, dye penetration. For internal and external surface, we may choose radiographic and ultrasonic examination, and finally surface and subsurface defect can be inspected by magnetic particle inspection and eddy current testing. While evaluating or commenting about the success of NDT, we can say just it is mostly interpret about our defect. It doesn't give a direct value. It doesn't give a strong result that we need to do this. But it depends skill, knowledge, and experience of the person performing this, and we can choose one method or combination of method, but we cannot coming into conclusions saying this that this method is superior to the other by competing with them, but it's always best to use a combination of them to get a better result and to predict much better about the quality of the casting. So thanks for your